Well, this brings us to the topic of absolute extrema. I may have already actually discussed this a little bit, but absolute extrema can occur at a boundary point of a domain or at a relative extremum point. So an example from Calculus 1 would be f of x squared has an absolute maximum of 16 on the interval between x is -2 and y is 4, because it never gets any more than 16 at that. The maximum occurs at a boundary point, but the function itself, if we didn't have that domain, doesn't have a maximum. It just keeps getting bigger all the time. So this could happen with functions of two variables, as the following example shows. I just want you to think hard through this.
Try to think, but nothing happens.
Well, you'll have that. So let's look at the absolute extrema for the function f of xy is 2x minus 2xy plus y squared. And so on the region, and our domain is the region between y equals 1 and y equals x squared. Thought I'd show you the region between y equals 1 and y equals x squared. That's this region, this little piece of the parabola. Boundaries are blue in this direction and red in this direction, so this part right here. So we'll solve simultaneously. Actually, I guess the first thing we should do is look at these partial derivatives. So partial with respect to x, 2 minus 2y. Partial with respect to y, negative 2x plus 2y. And so those are solved simultaneously. When this is 0, that happens when y equals 1. And when this is 0, that happens when y equals x. So 1, 1 is a critical point. Y equals x means if y equals 1, then so does x. And f of 1, 1 equals 1. So on the line y equals 1, with x between -1 and 1, we can write f of xy equals f of x equals 2x minus 2x plus 1, and that's 1. Think about why I'm saying that, because on that line y equals x. So I just replaced well, I'll replace my y. Well, y equals 1, so I replaced that, and so that's actually all I did, because I said on the line y equals 1, so I replaced y with 1, and I replaced this y with 1, so I got 2x minus 2x plus 1, and so I got f of x equals 1. So on the curve y equals x squared, we have f of xy equals f of x, 2x plus 2x cubed plus x to the 4th, that's x squared squared. This is 2x times x squared, so 2x cubed. And we can maximize and minimize that in the usual way. Find the derivative with respect to x. That's kind of easy. And so then we wind up with this situation. We need to solve this equation set to 0. So 1 is a root by the rational root theorem, and then we can divide out by x minus 1, and then we would get the other factors. So we get -1/2 and 1. 1 was actually a double root. So we got 1, 1 again, and also x is from this factor -1/2 and 1/4. Now, why is that so? Because if we're on the curve y equals x squared, then y equals -1/2 squared, so y is 1/4. So meanwhile, f evaluated there is this negative number. So after testing all our relative extrema and all the borders, we conclude we have an absolute maximum of 1 at the point 1, 1, 1, and an absolute minimum at the point -1/2, +1/4, Negative 11/16, by the way, where did I get the negative 11/16? That's a very good question. So let's go back to the original function. Where is it? Here we go. X is a half, y is a fourth, so this is 1 minus 1/4 plus, I'm sorry, 2 times, yeah, okay, 1 minus 1/4 plus 1/16. So I have here written negative 11/16, and I think that's wrong. Because if x is a half, so that's 2, no, it's negative a half, so that's negative 1, my fault. And this is plus 1/4 plus 1/16. So alright, that is correct. Negative 11/16. And so here's the domain, and here's the function that I hope I can describe pretty well as having, just remember, you have to think about this domain. We're only looking at the function above this parabola and below the line y equals 1. So y equals 1 is here, going this way, and the parabola is here, right? So if you can imagine, I can't draw that at the same time, but something like this. I'm trying to draw it with my little trusty pointer pen here. So that would be our domain, and so we have a maximum value of 1 at the point x is 1, y is 1 of 1, and so that would be here. And I think you can kind of see that. That's the biggest the function ever gets. And the smallest it ever gets on that zone is when x is negative a half, y is 1/4, and the function value is negative 11/16. So let's see if we can see that. X is negative a half, y is 1/4, and the function value, I'm going to have to look at it from this side, negative 11/16. So let's see, y is 1/4, x is negative a half. I can't really pinpoint the negative a half very well, but I think you can see the negative 11/16 roughly from the side. And that's more fun than I bet you've had with graphs for a long time.